Let's look at some examples where we are going to find the horizontal and vertical asymptotes of the curve. Our first curve is defined as y is equal to 4x minus 3 divided by 2x minus 1. Let's first find our horizontal asymptote. Since the power of x is the same in the numerator and the denominator, we can look at the limits as x goes to plus infinity and as x goes to minus infinity at the same time. The limit as x goes to plus or minus infinity of 4x minus 3, all divided by 2x minus 1, is equal to plus or minus infinity divided by plus or minus infinity. So we can just think of this as the indeterminate form infinity divided by infinity. Since we have the indeterminate form infinity divided by infinity, to evaluate this limit, what we're going to do is to divide the numerator and the denominator by the highest power of x in the denominator, which is just x. We'll write this then as the limit as x goes to plus or minus infinity, 4x minus 3 divided by x, all divided by 2x minus 1 divided by x. This is just the limit as x goes to plus or minus infinity. 4x divided by x is just 4. So we have a 4 minus 3 divided by x. And in the denominator, we have a 2 minus 1 divided by x. 3 divided by x and 1 divided by x are going to go to 0 as x goes to plus or minus infinity. So we just have 4 divided by 2, which gives us a limit value equal to 2. And our asymptote is y is equal to 2. Let's now look at our vertical asymptotes. To find a vertical asymptote, what you have to do is set the denominator equal to 0. Our denominator is 2x minus 1, so we're going to set that equal to 0, and then we'll solve for x, and we get x is 1/2. And that is our vertical asymptote. I've graphed this function so that you can see that the horizontal asymptote is indeed y is equal to 2, and the vertical asymptote is given by x is equal to 1/2. Let's now look at our second example. This example is a bit more complicated than the first one. We're going to begin again by looking at the horizontal asymptote first. Since the numerator and the denominator contain different powers of x for their leading terms, and they're both not even powers, we need to look at the limits as x goes to infinity and x goes to minus infinity separately. Let's begin by looking at the limit as x goes to positive infinity. We're going to divide both the numerator and the denominator by the highest power of x in the denominator, and that's going to be x squared. Let's plug in x to see what we get. On the top, we have infinity cubed minus infinity, and then on the bottom, we have infinity squared minus 6 times infinity plus 5. So what we have on the top is infinity cubed because that's much bigger than infinity. And then on the bottom, we can write this as infinity squared. That's the highest power. So this is going to equal infinity. Now, you can take a more algebraic approach to solving this and divide both the numerator and the denominator by the highest power of x, and you'll get the same answer. Let me just go ahead and do that so you can see. Honestly, sometimes it just depends what your instructor is asking for, which way you have to do it. We're dividing the top and the bottom by x squared, so this is 1 minus 6 over x plus 5 over x squared. This term goes to 0, as does this term and this term. So we're left with the limit as x goes to infinity of x, which is just infinity. And that matches what we got earlier. Now let's look at what happens as x approaches minus infinity. We have x cubed minus x, all divided by x squared minus 6x plus 5. Let's plug in x goes to minus infinity. We'll have to watch our negatives here. We have minus infinity cubed minus infinity, all divided by minus infinity squared minus 6 times minus infinity plus 5. These two terms are our largest terms, so we can ignore all the other ones. And this gives us a minus infinity cubed divided by infinity squared, which gives us minus infinity. So that's our answer. Again, you can get that answer by dividing both the top and the bottom by x squared. Now let's think about what our answer tells us. We found that the limit as x approaches infinity and minus infinity is infinity and minus infinity. That tells us that we actually have no horizontal asymptote. Let's now look at our vertical asymptotes. To find the vertical asymptote, we have to set the denominator equal to 0, but there's a catch. We can only do that after we factor out terms that are common to both the numerator and the denominator. So we're going to have to start by factoring the numerator and the denominator. We have x cubed minus x, all divided by x squared minus 6x plus 5. In the numerator, we can pull out an x, so that leaves us x squared minus 1. And then in the denominator, we can factor this as x minus 1 and x minus 5. Notice that in the numerator, we still have a term that needs to be factored, so let's do that. That's x. X squared minus 1 factors into x plus 1 and x minus 1, and then we'll copy down the denominator, x minus 1, x minus 5, and now we can cross out the terms that are common to both the top and the bottom. What we do next is we take the term in the denominator that's left and we set that equal to 0. And that is x is equal to 5, and that is our vertical asymptote. I graphed this function so that you can see that it has a vertical asymptote at x is equal to 5. And I also wanted you to notice one other thing. Do you see this open circle right here? That is called a removable discontinuity. And it happens when you have a function where you can factor out a term such as x minus 1. This function also has what's called a slant asymptote. That often happens when you're finding a horizontal asymptote and you get that it goes to infinity. And that's it.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.